In the history of science, few phrases carry as much weight as Albert Einstein calling something his biggest mistake. The admission has echoed through decades of popular science writing, documentaries, and textbooks. It refers to a single mathematical term Einstein introduced into his field equations of general relativity, the cosmological constant. The story usually unfolds as a simple narrative. Einstein added the constant to preserve a static universe, discovered he was wrong, and regretted the decision for the rest of his life. But this version of events, while dramatic, omits crucial context. The cosmological constant was not the product of stubbornness or miscalculation. It emerged from the best available evidence of its time. What Einstein called a mistake was, in reality, a decision made with incomplete data, a distinction that fundamentally changes the meaning of the story. The true narrative is not about error, but about the limitations inherent in any scientific endeavor. It reveals how timing, observation, and evolving knowledge shape even the most brilliant minds. In the early 20th century, the prevailing astronomical view held that the universe was static and unchanging. This was not mere assumption. Observations showed stars moving within the Milky Way, but no indication suggested the cosmos itself was expanding or contracting. The universe appeared stable, eternal, and fixed in scale. When Einstein completed his general theory of relativity in 1915, the equations described how matter and energy curved spacetime. The mathematics were elegant, revolutionary, and immediately problematic. The field equations predicted that the universe could not remain static. Gravity would cause all matter to collapse inward unless something counteracted that pull. The equations demanded either expansion or contraction. This posed a direct conflict with astronomical consensus. Observers saw no evidence of universal motion. The cosmos appeared still. Einstein faced a dilemma. Either his equations were incomplete or the universe behaved in ways no one had yet detected. Neither option was satisfying. The theory of general relativity had already passed critical tests, including the precise prediction of Mercury's orbital precession and the bending of starlight during a solar eclipse. The mathematics worked, yet the cosmological implication contradicted observed reality. Einstein needed a solution that preserved both the integrity of his equations and alignment with empirical data. The answer had to be mathematically sound, physically plausible, and consistent with what astronomers reported seeing through their telescopes. Einstein's solution came in 1917 with the introduction of a new term into his field equations, the cosmological constant, represented by the Greek letter lambda. This was not arbitrary manipulation. General relativity permitted such a term without violating the mathematical structure of the theory. The constant represented a form of energy inherent to space itself, exerting a repulsive force that counteracted gravitational attraction. By carefully tuning the value of lambda, Einstein could construct a model where the universe remained static. The repulsive force balanced gravity perfectly, preventing collapse or expansion. The cosmos could sit in equilibrium, unchanging over time, just as observations seemed to indicate. Mathematically, the addition was consistent. Physically, it introduced a new property of space-time, but one that could not be immediately tested or falsified. At the time, this modification appeared reasonable. Many physicists viewed it as a natural extension of the theory rather than a fundamental alteration. Einstein himself was cautious, but pragmatic. The cosmological constant solved the pressing problem, and did so without contradicting any known observations. In the absence of evidence for cosmic expansion, the static model offered a coherent description of the universe. The scientific community largely accepted the solution. It reconciled theory with observation. It preserved the elegance of general relativity while accommodating the apparent stillness of the cosmos. For over a decade, the cosmological constant remained a standard feature of cosmological models. In 1929, astronomer Edwin Hubble published observations that fundamentally altered cosmology. Using data from distant galaxies, Hubble demonstrated that these galaxies were moving away from Earth. More significantly, the farther away a galaxy, the faster it receded. This relationship, now known as Hubble's law, provided clear evidence that the universe was expanding. The implications were immediate. If the universe was expanding, it did not need a cosmological constant to remain stable. The original field equations of general relativity, without the lambda term, naturally predicted expansion from an initial dense state. The observations aligned perfectly with the unmodified theory. Einstein recognized the significance almost immediately. The cosmological constant, introduced to prevent expansion, was no longer necessary. The universe was not static. The assumption that guided the modification had been wrong. In private correspondence and later discussions, Einstein expressed regret over the introduction of lambda. He reportedly referred to it as his biggest mistake, though the exact context and phrasing of this statement remain somewhat uncertain in historical records. The scientific community quickly moved away from the static model. Expanding universe cosmology became the dominant framework. The cosmological constant, once seen as an elegant solution, now appeared superfluous. Einstein's characterization of the cosmological constant as a mistake must be understood within context. He was not admitting to a fundamental error in reasoning or mathematics. The introduction of lambda was methodologically sound, given the available data. Astronomers reported a static universe. General relativity predicted instability. The constant resolved the discrepancy. The mistake, as Einstein saw it, was adding unnecessary complexity when the simpler solution, trusting the unmodified equations, would have been correct. Had he resisted the temptation to force agreement with contemporary observations, the theory would have predicted cosmic expansion before Hubble observed it. This would have been a triumph of theoretical prediction over empirical expectation. But expecting Einstein to ignore astronomical consensus would be unreasonable. Science progresses through the interplay of theory and observation. When the two conflict, adjustments are necessary. The cosmological constant was not a failure of intellect. It was a reflection of incomplete information. Einstein worked with the best evidence available. That evidence later proved insufficient. What the episode reveals is the inherent uncertainty in scientific judgment. Even the most successful theories operate within boundaries set by observation. When those observations change, conclusions must change as well. Einstein's regret was not about making an error, but about missing an opportunity to trust his equations more fully. The distinction matters. One represents failure. The other represents the normal tension between theory and data. For decades, the cosmological constant remained largely forgotten. Expanding universe models did not require it. Cosmologists focused on measuring the rate of expansion, the density of matter, and the geometry of space-time. Lambda seemed like a relic of outdated thinking. Then, in the late 1990s, two independent research teams studying distant supernovae made an unexpected discovery. The expansion of the universe was not slowing down, as gravity would suggest. It was accelerating. Galaxies were moving apart faster over time. This acceleration required an explanation. The most straightforward solution was to reintroduce a cosmological constant-like term. This time, it represented dark energy, a form of energy permeating all of space, exerting negative pressure that drives accelerated expansion. The mathematics were nearly identical to Einstein's original constant. The physical interpretation had changed, but the fundamental role remained the same, a repulsive force counteracting gravity on cosmic scales. Observations from cosmic microwave background radiation, galaxy surveys, and large-scale structure confirm the existence of this dark energy. Current models suggest it comprises approximately 70% of the universe's total energy density. The cosmological constant, once discarded as a mistake, had returned as a central component of modern cosmology. The irony is difficult to ignore. Einstein introduced the cosmological constant to maintain a static universe, a purpose later rendered obsolete by observations of expansion. He called it a mistake. Yet decades after his death, cosmologists reintroduced a nearly identical term to explain accelerating expansion. The constant was not wrong. It was premature. This distinction reshapes the entire narrative. Einstein was not mistaken about the physics. He was working with insufficient data. The static universe assumption was the error, not the mathematical framework he constructed to accommodate it. When that assumption fell away, so did the apparent need for lambda. But the universe itself had other plans. The story illustrates a fundamental aspect of scientific progress. Timing matters. Ideas that seem unnecessary or incorrect at one stage can become essential later. Theories are judged against available evidence. When evidence changes, judgments change. Einstein's mistake was not a failure of imagination or rigor. It was a consequence of operating within the constraints of his era. The story of the cosmological constant is not a tale of error. It is a reminder that science unfolds through layers of discovery, each building on incomplete understanding. Einstein worked with the knowledge available in the early 20th century. He made a choice that reconciled theory with observation. Later evidence changed the context of that choice. What this reveals is the provisional nature of scientific conclusions. Even the most elegant theories must adapt to new data. Even the greatest minds operate within the limits of their time. The cosmological constant was not Einstein's biggest mistake. It was a decision made in the absence of complete information, a condition that applies to all scientific inquiry. The universe does not reveal itself all at once. Understanding emerges gradually through observation, revision, and patience. Einstein's cosmological constant, discarded and resurrected, stands as evidence of that process. The mistake, if there was one, was not in adding the constant. It was in believing the question had been settled.